Okay, so we're still in chapter 3. We're still talking about scheduling. And last week, we talked about what we called batch processes and some of the scheduling approaches that work for batch processes. And you'll recall that batch processes are processes that are mostly non-interactive. They don't need any input. They don't receive any input from the user. They don't have to respond to the user. So we run them, we let them go, okay? And then they finish in a certain amount of time. So that's kind of an oversimplification of what we usually expect out of computers and what we usually expect out of processes in general. More often, we are dealing with interactive processes, okay? Processes that are going to be taking requests, so take requests, process those requests from the user, and respond to requests, right? And repeatedly doing this, and having multiple processes that are doing this all, quote unquote, simultaneously. That's generally the kind of process that we're looking at when we're talking about modern computers. And this changes our objective just a little bit, because now it puts an added weight on getting throughput, okay, in the system, having maximum throughput through the system. Right? This is the notion that I'm going to answer as many interactions in as short a time as I possibly can, okay, to make the user feel like the system is responsive, okay, as opposed to merely focusing on processor load, making sure that the processor usage is close to 100%. There's still a balance. There's a balance to be struck here. And we'll talk more about and kind of define what that balance is in just a second, after we look at some possible algorithms that will do this kind of scheduling, this kind of interactive process scheduling. The first of those algorithms is called the round-robin scheduling algorithm. Okay. Round-robin schedule. Okay. Who knows what a round robin is or what that term refers to? You generally hear it, at least in the United States, or I did as a kid growing up, when dealing with sports and tournaments in sporting tournaments, okay? Round robin simply means that all the teams play each other. They take turns playing each other, right? So you can think of this as taking turns. I actually got curious and looked up the etymology of the term round robin. And like so many other things in English, it's a bastardization of a French term. And I don't remember what the French term was, but that's why it has nothing to do with the bird, right? It's just called round robin, okay? And you can think of it as taking turns. So what does round robin look like? It looks like this. It is based on a queue, okay? So there's a single queue that feeds our processor. And this is my best attempt at drawing the graphical representation of a processor. Okay? Feeds a processor. And this single queue, like most queues, is first in, first out. Okay? So it's the order in which processes get processed, get access to the processor, is first come, first serve. Okay? With the added wrinkle that there is this notion of a time quanta or time quantum. Okay? This is a period of time, say 10 to 100 milliseconds, or microseconds, that during which the current process can run. Okay? So a process arrives. If the queue is empty, it immediately goes onto the processor and runs for your time quanta period of time. Okay? During that time, as it's running, you might have other processes arrive. Okay? And they just line up, waiting to be run. Now, all of these processes are either new processes or they are ready processes that have been processed a while ago. Okay, so in my world, all these are new processes. Okay, but when a process runs out of its time quanta, it gets kicked off of the. Let's use this. It gets kicked off the processor, and it gets added back to the end to wait its turn again. Right, so this one's already been served. To wait its turn again for its chance to get back onto the processor. Anything that appears after that, well, it goes to the back of the line. There's another one that's waiting in the back of the line. Okay? So this is strictly first come, first serve. You get access to you get context switched onto the processor for a time quanta time, as long as you're ready. This queue does not contain any blocked processes. These are all ready processes. Okay, as long as you're ready, you get moved onto the quanta for a period of time, and then you get moved off of the not moved onto the quanta, but moved onto the processor for a quanta of time, and you get moved off if you're not done yet. If you're done, then you leave the system. Okay, you exit. Your process is done. So this has the notion, so the pros here, this has the notion of being quote unquote fair, right? Everybody is going to get a turn. Everybody is going to get the same amount of time every time they jump on the processor, right? That is not to say that all processes take the same amount of time to run, right? Because the process takes the amount of time that it takes. Right? The operations take the amount of time that they take. And if they get blocked, they get blocked. That's a whole other thing, right? They got to wait somewhere else to become unblocked. But what it does mean is that if you get on the processor, you have a set amount of time that you can run on that processor before it becomes somebody else's turn, some other process's turn. Okay? It also, on the pro column, it has no starvation. Okay, so what does the term starvation mean?
Lack of resources.
Lack of resources, but specifically what resource are we talking about? So what? Time on the processor, did somebody say that? Okay. Masks, air conditioner, be bold. I can't hear you necessarily. I'm old. You have to speak up. So time on the processor is specifically the resource we're talking about. If you don't get processed because it never becomes your turn, then you are said to be starving. You are suffering from starvation. Okay? I don't want you to think of starvation as a binary. You either are starving, you either do starve or you don't. It's a state in which you become more and more starved for time on the processor, okay? This, because everybody gets the same amount, priority. Everybody gets the same access to the processor. We're guaranteed that no processes are gonna become starved. They're all treated equally. Is that good? No, we've already kind of talked about this notion, right? So the con list over here for this approach is that there's no workable definition of priority, processor priority, right? All processes have the same priority in this setup, so there's no priority. If everyone's special, then no one is. Okay? None of the processes can be taken as more important than any other process, meaning that they should get the processor first. Okay? So nothing that we can know about these processes changes that. Nothing about the time constraints that a process might be under. Nothing about this kind of thing where we want to take requests, process requests, and respond to requests as soon as possible. Okay, nothing about that gets baked into the design of this schedule. Okay, so that's the biggest con. Now this is really simple. It's fair. There's no starvation, but it doesn't really meet our needs when it comes to interactive processes, because we can't force processes who are on a deadline to be able to go ahead of other processes. Okay? Does that make sense? Now, let's go to the next. This would be the multi-level scheduling algorithm. Or the ML scheduling for short. What if we had a bunch of queues? In fact, we're going to have n total queues, okay? Let's call this level 1. And there's even in the literature, there's some people call level 1, and they refer to level 1 as being top priority. That's how I like to think of it, and not level n being top priority. But you can understand that, like, sometimes people think that the higher the level number, the more priority you have. I think the lower the level number, the more priority you have. But either way, it's symmetric, okay? So this is level 1, and then here's level 2, and here's level 3. Each of these gets their own queue, so forth and so on. There's so many more of them. And then there's level n for the lowest possible priority. Lowest possible priority. And so what this does is it reproduces the round robin, the effect of a round robin queue, but with multiple queues where the level you go into as a process determines is determined by your priority. Okay, so top priority processes. Here, this is a process. It arrives. Okay, so there's nothing running on the processor. It immediately gets to go. Okay, you still have this notion though of a time quanta. Okay, whatever it is, let's call it Q. Right? You have this notion of a time quanta. This guy arrives. The processor's not doing anything, so it immediately jumps on there, and it's going to run for Q microseconds. In the meantime, while it's running, another process arrives, and it's not a top priority process. It is let's say it's a level 2 process. Now, how do we determine if it's a level 2 process or a level 1 process? Well, you'll recall from our discussion, even with batch processes, that some of them are higher priority processes than other, and we talked about ways that you can statically and dynamically determine a process's priority. So those kinds of decisions and algorithms are still in play here. Okay, let's just assume for argument that we know what the priority is, or that we can at least tell what the priority is. we've already talked about how to do that. So if you have questions about that, review those notes from last week. All right, so also still the yellow guy is running, okay? And then a blue, this guy arrives, okay? Now the time quanta is up, so this process is not done, so he re-enters at his original level, okay? Processor is ready to load something else in. Where should it load from? Blue's ready to go, green's ready to go. Where should it load from? The top. That makes sense because we're doing this in deference to priority. We want the top priority things to be able to go first. And since there are still things in the top level, in the top level priority queue, we're going to put those things onto the processor. Okay? And this guy may finish or he may go back to the back of the queue, but effectively, as long as there are processes on this to be run, then they are going to split time on the processor using Q quanta each time until they're all done, okay? In which case we're going to go, if this is empty, then we're going to go pick things from this queue, okay? And then at such time when this queue is empty and this queue is empty, then we're going to pick things from this queue if there's anything there, right? This poor process, though, is the lowest priority. Okay? So all of these processes are still running at time quanta Q. Okay? So you can see how this has a pro. The pro of this is that it defers or it respects, let's say it respects priority. Okay? So I don't know. We have to be careful what we mean by fair. This still seems fair, right? Especially if we care about priority. Okay, and the biggest con about this is what?
Lots of memory, horsepower, lots of.
Yeah. Okay. That's fine. I mean, you need more space to keep up with all these queues. That's true, and a lot of them might be empty some of the time. So yeah, I hadn't thought about that, but yeah, as a memory efficiency matter, it's worse. Yeah, that's absolutely true. No, it's not what I was thinking about though. What about this guy? What's likely to happen to him? Yeah, it may or may not get run. Things are arriving in this system all the time. Okay? Things are arriving in this system all the time. This guy has to wait, guaranteed has to wait for all things with higher priority that arrive before he finishes to finish before him. Okay? And that even if all these levels clear out and he miraculously gets to go on the processor, he only gets to run for one time quanta, and then he's back down here, okay, waiting again. Okay? So the biggest drawback is that this really suffers pretty greatly from starvation. Okay? This guy has to wait for all other higher priority things that might arrive to run, and he has to do that potentially multiple times if he can't finish in one time quanta. Okay? Does that make sense? All right. So can we do something better that kind of balances those two, the pro and the con there? Can we kind of try and balance that? Well, yeah, this is our attempt right here. It's called multi-level feedback scheduling. Multi-level feedback scheduling. Yeah. or MLF scheduling. So in this case, it looks pretty similar at first blush to multi-level scheduling. We've got, again, top level, level 1 priority, followed by another queue for level 2 priority, and then level 3, okay, and then however many there are, and then level N priority is down here. Okay. And we've got only the one processor that can handle only one process at a time. So that's our standard. And these things are tied to the processor in much the same way as before. Okay. With a difference, a couple of differences. Still, you have the notion of a time quanta, and let's call it Q. All of the things that leave level 1's priority queue and go into the processor get to execute for a time quanta of Q. All of the things at level 2 get to execute at 2Q. Okay? All the things at level 3 get to execute for 4Q. So their time quanta is 4 times bigger than level 1. Okay? So forth and so on, down the levels until you get to level N, and things that are on level N get to monopolize the processor until they're done running. So they have effectively an infinite time quanta. Okay? They get to run until they are done. Right? Already with this, right, you begin to see something that that multi-level scheduling didn't have. If there's some poor guy down here, okay, if there's some poor guy down there that doesn't ever expect to be able to run until all of these higher priority processes above him are finished, at least when he gets the processor, he's guaranteed to be able to finish and not to have to go back into the lowest level again. Okay? So already this helps address the problem with starvation from multi-level feedback. Does that make sense? Yeah?
But shouldn't the highest priority get like more time?
No, because they're going to get on the processor more often. Yeah? Right? And I understand what you're saying. You're like, we want to push those things through. If we want to push them through in such a way that we still don't starve anybody. Right? So we're balancing those concerns. Okay? So there's one more thing that makes this even more interesting. Let's say a high priority process arrives. Okay, he gets to go onto the processor for Q time period. So he's on the processor. In the meantime, this process arrives here. He's second level. Okay, and also while this guy is still running, he goes and another process appears right here. Okay, there's a slide. This is the feedback part of this. If this guy who's on the processor right now does not finish, okay, before his time quanta is over, time quanta Q, he doesn't go back here. Instead, he slides, this is difficult to draw, so you'll have to bear with me, but he slides back to the lower, to a one level down. Okay? Okay? So he doesn't go back into the top level queue. Instead, he leaves the processor and appears right here. Okay? Yeah. Now, you say, well, he's still a high priority thing. We want to get him to go, right? But we don't want, he's already had a chance. So he's already done some processing, right? We'd like the other highest priority things to be able to go now, okay? when it comes back to this original top priority thing, he's going to have twice as long to process the next time he gets on the processor. Okay? So at this stage, after this guy has been on the processor one time and he's not finished, he's bumped down to the next queue, he appears there. Now who do we pick to go on the processor? Tell me a color. No, not green, because there is a process that is a higher priority than green. Okay, so we're going to put blue on the processor, and blue gets to go for a time quanta of Q, and if he does not finish, then he's going to end up reappearing in the queue below. Okay, now who do we pick? Green. Green this time. There's nobody in the highest queue. The next higher queue has processes in it, so we pick green. Okay, so we're going to pick green and move him out of this queue onto the processor. Let's say he finishes. Okay, great. He was able to finish within 2Q time on the processor. Okay, now who do we pick? Well, yellow. Okay, because yellow is left at the front, and we add yellow here. He runs for 2Q, but he doesn't finish. Where does he end up? Level 3. Okay, and he ends up down here. Okay, their feedback. The feedback about how long they're going to take to run, right, keeps telling us more about how long we should be adding to their quanta, right, as they get lower and lower priority. Right, so this is an attempt to balance the need to process high priority things more often, but things that need more processing get more processing time between being on the processor. Each time they go on the processor, they get more time. Eventually, if this guy keeps trickling down and he gets more and more time, he'll eventually end up at the bottom here, right behind the lowest processed thing. And if all of this is eventually cleared out, right, then we'll run this one until it finishes, and then we'll run this one until it finishes. Okay, as long as new processes haven't arrived. Okay. All right, so I would say that this is a balance, okay, between our need to support priority and our need to not have starvation. Could starvation happen in this scheme? Okay, I'll accept that as a correct answer. Now tell me why.
If the starvation would happen, let's say yellow keeps going from level 1 to level 2 to level 3, and they just keep repeating on every levels.
Yeah.
Even level N, you might not get to level N.
Yeah.
Unless it takes like maybe a week or
Yeah.
two.
Okay. So the load on our system could be so much that we can't process these low priority things. Okay, that could happen. But do you see that the likelihood and the severity of this kind of starvation that might happen here is a lot less severe than the kind of starvation that could happen here, right? We're taking steps to abate that kind of starvation. We can't rule it out, short of doing something like this where everybody just takes a turn and we don't have the notion of priority. Because as soon as we support a notion of priority, then you can imagine a system where it's being slammed with new processes all the time of high priority, okay? And the throughput, the fundamental amount of processes, the basic amount of processes that the processor can deal with is insufficient to deal with all of those, and we still get starvation, right? But the only way to not have that is to not have the sense of priority at all, and just let them come one at a time, one after another, and that's not what we want. So as soon as we start dealing with priority, then there's a chance of starvation, but some schemes deal with starvation better than other schemes. Okay? All right, any questions about that, about any of that? So I want to talk about another sort of design trade-off. Right? It comes with scheduling. And it's the trade-off or the balance between throughput and quanta size. Okay. We said that interactive processes have to do three things. They've got to receive requests. They've got to process those requests or do some processing as a result of those requests. And they have to respond to requests. And the thing to notice about this is that the process must be running to do any of those things. Okay? The process has to be on the processor to receive a request, and it has to be on the processor, obviously, to process a request, and it has to be on the processor to respond to a request. Okay? So what does that mean? Well, let me ask you a related question. Should we have, do you think it's better to have large quanta or small quanta? Now, I don't want you to get confused about this because, yeah, the quanta updates at each level, but we can still answer the same question about that fundamental quanta, that basic quanta that determines what all these other values are. Okay? So should we have generally larger quanta or generally smaller quanta? Which is more effective? Okay, so we'll go with small quanta first. All right, so here's let's do small quanta. Now, why? Okay, so that means the smaller the time frame, okay, the more processes we process during a set amount of time. The other way to think about this is the smaller the time frame, as the time frame gets smaller, we maximize the number of context switches. Okay? Maximize the number of times that we move one process off the processor and put another one on. All right, what's the problem with that? Well, it depends on our scheduling. Depends on which scheduling we're using. Okay, so let me put this down. Let me put this down in big red letters. There. Well, let's scratch that. I can do better. Context switching is expensive, right? And more precisely, context switching takes a significant time. Because what are we talking about? What are we talking about when we say context switching? Because it was like, I've waved my hand at it a little bit and said, well, context switching is when we take one process off the processor and we put another process on. But what that means precisely is stop executing the current process's code. Store the current process's stack pointer, its stack values, its entire stack, its program counter, store its all the registers as they currently sit, what we're doing right now, store the operations, right? Store the instruction somewhere. Store all that, copy all that stuff to some place else where we can remember it. Update the PCB off so it moves off so we can remember where all that stuff is, okay? And then pick up a new PCB and read out of that process control block what the last time this new process ran, what was the process counter? Copy that over. What was the stack pointer? Copy that over. What did the stack look like? Copy that over. What did each of the registers look like? Copy each one of those over, okay? Then and only then can you begin to execute, again, that new process that just got switched onto the processor, okay? So that's what I mean when I say that this is expensive and that it takes a significant amount of time, okay? None of that is what we would call a good use of the processor, right? It doesn't achieve anything except swapping processes. It doesn't actually push any process forward toward conclusion, right? So, yeah, you're right. You're right. Having a small quanta means that we get to see, the processor gets to see more processes in a shorter amount of time, but it also maximizes the wasted amount of time that is required to do all of that swapping. Okay? Right? Does that make sense? So something that could happen, let's say potentially a worst case scenario. And I freely admit that this is a worst case scenario, and this doesn't have to happen to us. But our computer is going to be judged by its worst case performance, right? This is maybe something that you don't know about human psyche, but you remember bad things way more clearly than you remember good things, okay? And so if the computer is occasionally making your life hard, you're very quickly going to start to remember all the times that it made your life hard, way more than you remember any time that it didn't, okay? So we're going to be judged by our worst case performance here. So let's say this happens. Let's say we've got a program, okay, and it needs to receive a request during its lifetime. It needs to receive a request. It needs to process that request, okay, and then it needs to respond to that request. And roughly speaking, this block is a proportional amount of time that it takes to do those things, okay? If we have a small quanta, right, then this process is going to be carved up into small chunks of time, maybe all the same, again, depending on our scheduling, maybe all the same quanta, so that this chunk of processing goes on the processor, and then this one does, and then this one does, right? And then it gets carved up. And the wait time between two consecutive periods of time on the processor is maximized, right? Because we are seeing as many, not only are we shrunk down, not only is our process time shrunk down because our quanta is minimized, but the wasted time between us being on the processor, between consecutive instances of us being on the processor, is maximized, right? Other processes get to go before I come back, plus they all have that context switching overhead. Okay? What happens if I receive your request and then I get pulled off of the processor? From the user's perspective, what happens? If the process receives your request and then gets pulled off the processor, what's that going to look like? What's that experience going to be like for the user? Eventually, you're going to get put back on and you're going to get to process that chunk. And you're going to get pulled off again. And you're going to get put back on eventually, and you're going to get to process that chunk. You're going to get pulled off again. What's the user doing while I'm processing and waiting and processing and waiting? What's the user doing? The user's sitting there. What is going on? Why is this taking so long? Right? Because the user doesn't understand that other processes have to go. It also doesn't understand that this amount of processing time has to happen, right? All the user cares about is, have you received my request? Okay, I gave you a request. When do I see this? Okay? And so the more we carve this up, the worse that possibility gets, and the more time it takes to wait to get that processor up and running. Okay, the more wasted amount of time, wasted processor time there is. All right, does that make sense? Now, all I did was let you pick small quanta, and I don't think it's an irrational thing to say, hey, the smaller the quanta, it feels like the better off we're going to be. And I say that because had someone said large quanta first, right, we still would have had problems, okay? Because as the large quanta increases, right, we also, as the size of the quanta increases, right, it's still possible that there could be a large wait time between my processing and my responding. Okay? Again, here's another worst case scenario. Here's that same process again, and we've got the receive request, the process request, okay, and the respond request. Now we're carving this up into huge chunks, okay? The worst possible thing that could happen to us now is we lose the processor right there, okay? So we receive the request, we process the entire thing, yet we still don't have a chance to respond, okay? And now we've maximized the amount of time that we're waiting on other programs to run. Okay? Because we've increased the quanta for other programs, right? This is still no better. Okay, it's no better than previous. All right. There's no magic bullet solution that fixes this. Okay. The answer is that this is always going to be a trade-off, and it's always going to be a balancing act that you have to, as potential future scheduling algorithm designers, you have to wrestle with. Okay? Does it look like your system has a lot of short-running processes? Well, if you knew that, then you might lower the quanta without any problem. Does it look like your system has a lot of long-running processes? Like the user's asking you to do a lot of things, it's going to take a lot of processing, okay? Then you might tune that by changing the quanta, okay? And this also gives you an additional tunage, way to tune this, because there's nothing magical about 2Q and 4Q and 8Q and so forth and so on. You could play with those numbers as well, okay? Based on what kind of system you have, you might do some research to study what kind of increase here makes the most sense, gets us the most throughput for a certain kind of system, okay? Those are exactly the kind of research questions that computer scientists love, because there is no way to optimize this in the general case. You can spend a lot of time trying to optimize this for specific cases and saying, well, this seems to work under these circumstances and this seems to work under these circumstances. And then once you have those, you can kind of try and make the more general argument that one kind of thing is better than another. And you may recall from early on this semester when I said that operating systems are not done evolving, right? Well, scheduling algorithms have to evolve right along with the kind of operating systems that we have. So these are open questions, open balancing acts that are going to be problems for designers on into the future. Okay. Any questions about that? Either the algorithms that we talked about or the sort of balancing thing, the balance considerations that we have to make.
Scheduling is used in Windows 10.
Oh, that's a good question. I don't know. I'll tell you that as far as a schedule is concerned, the schedule algorithms I've given you are oversimplifications, and that there's generally going to be a combination of real time, which we're going to talk about in just a second, and interactive processes that get scheduled in different ways. So you don't have to be only multi-level feedback, right? You can mix and match your schedules based on what you see out of the performance that you get.
Just multiple algorithms working side by side.
Yeah. Well, effectively what it is the scheduler says, okay, what kind of process is this? All right, I'll put you over here and I'll run this algorithm to schedule you. Okay, what kind of process is this? All right, you're a different kind of process, so I'll put you over here and I'll let that algorithm run you. And so the scheduler is running combined algorithms, right, to decide out of all of that which one gets the processor. And it's got to do it, at superhuman time frames, super fast. Yeah. I don't know what Windows 10 does specifically, and I don't know that anyone outside of Microsoft knows what Windows 10 does specifically. Yeah. All right, so our next topic then, I mentioned it just a second ago. These are real-time processes. These are processes that need to be done within a deadline. Okay. Can you think of some contexts in which you might have processes that need to process within a deadline? Okay. Yeah. So airplane. And this is called fly-by-wire. But not just airplanes, by the way, also cars, because what you do on a daily basis can be correctly called drive-by-wire, right? When you press your brake pedal is not physically connected to the braking mechanism of your car. It is a switch that is used as input to your car's computer. And your car's computer has all of its sensor input plus the notion that you press the brake. It then decides, based on how hard you press that brake, how hard it should brake, right? Because your meat brain is dumb. right? You say, I need to stop now. And so you slam on the brake, okay? But if you've ever done that, then probably what you've experienced is not like a sudden stop, but like your car has gone and stopped like that. That's the analog braking system that's working for you. Because if you slam on your brakes, the braking system is capable of locking up your tires. But if you're going down the road and your tires lock up, what's going to happen? You're going to slide off the road and wrap yourself around a telephone pole, okay? So instead, the computer says that's not what we want to do, okay? Even though they're pressing on the brake very hard. In this situation, that's not what we want to do. I have decided instead that the mechanism will tap the brakes. Tap, 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 right? And thus balance the risk of sliding with the distance that you need to stop in, okay? Not only that, but your steering wheel. Your steering wheel is not attached to the tires. Your steering wheel is a control, right? It's a sensor that you put input into, and the computer decides based on how far you've turned it and other circumstances how much your tires should turn. In old cars, you used to be able to put them in neutral and spin the tire with the steering wheel. New tires don't do that. I mean, new cars don't do that with the steering wheel. You can put it in neutral and spin and spin and spin, and the tire doesn't move because the computer's not on and your steering wheel is not attached to your tires. Okay, this is drive-by-wire. We want the system that determines which direction our tires are facing to be fast. That analysis has to happen within a deadline. It doesn't have to be life and death, though. It could be streaming video, or teleconference video, right? That kind of processing needs to happen. So this video that's being recorded right here, it's not actually being streamed anywhere because there's nobody hooked up to see it, but it's going out to the Zoom server, right? But before it goes out on the internet, the application on this machine compresses it so that it can be sent more easily, right? And then it gets decompressed on the other end for people to see it. Well, if that doesn't happen, if you don't compress the frame within the amount of time that you have to send it, and you don't decompress the frame within the amount of time you have to see it, then it's going to look like, and colors are going to be all weird, and you're not going to be able to see what I'm doing, right? This is real-time process. Okay, real-time processes, and they're on the internet. They're everywhere. Okay, real-time processes have a deadline. More importantly, we think of the notion of a period. This is the time within which a process must be completed. Okay, so if a process arrives in the ready queue at time X, it must be done by X plus its period. Okay? Does that make sense? That is different than its runtime. Okay? These are two different concepts. If this is its period, okay, it arrives here in the system, it must be done by here in the system. This might be its runtime. And you should think of this runtime as being able to slide that direction, okay? And it could be carved up during that period as well. In other words, you might do some part of it, then go off the processor, and then this slides down this way as time elapses, and then you can do the last part of it. As long as it's all done by this point, then we have met our schedule. Okay? Does that make sense? All right, so what does that mean? What does that mean for our scheduling algorithms? Well, we need some new ones. We need some new scheduling algorithms for this. The first of them is the rate monotonic algorithm. Oh, you guys can't see this. Yeah. Rate monotonic schedule. Basically what that means is the shorter the period, the higher the priority. okay? Shorter the period, the higher the priority. Now, recall, we have this notion of a process that needs to run in a given amount of time. And here are two such processes, and maybe this process is going to be repeated a couple of times, okay? And this guy takes this amount of time. This is his runtime. Okay, that's his runtime right there. And this guy takes this amount of runtime. Okay? Which one of these two processes is going to have the highest priority according to the rate monotonic schedule? Which one? Green. Yeah, green. Why does that seem not quite right? Well, it might be, but let's assume that that aside from that, all their other priorities are the same. It's really the priority, the chief priority is you got to finish in time. Notice that this guy has no time to wait, no time to waste, whereas this guy has plenty of time to waste. Okay? He can wait a little bit, right? And so what might end up happening with rate monotonic scheduling is we could pick a algorithm with a shorter period, but with much more flexibility, okay, over an algorithm with a longer period, but less flexibility, okay? And this is not going to guarantee an optimal outcome, right? So let's look at a different potential algorithm. Let's look at earliest deadline first algorithm. Earliest deadline first, right? Or EDF, earliest deadline first. What that does, the shorter the remaining time, the higher the, oh, you can't see it. Yes, thank you, EDF. The shorter the remaining time, the higher the priority. Okay, the shorter the remaining time before the end of the deadline, the higher the priority. Okay? So the shorter that I have to finish, the higher priority I have. And I can go ahead and tell you that under certain circumstances, under circumstances where there is a schedule that's possible, this algorithm will generate an optimal schedule. Now, that said, it's not always going to be that a schedule that meets the deadlines is possible. Okay? So let's look at this. What is this notion of feasible? Okay? Feasible means that a deadline that deadlines for all processes can be met. Deadlines for all processes can be met. So as long as the set of processes and their deadlines is feasible, then EDF is going to generate a feasible schedule. Okay? It's going to generate a feasible schedule every time. How do we know if a set of schedules is feasible or not? Well, let's take, here, I'll just show you instead of rewriting this. You can take T sub I, so T sub I, right? That's the total CPU time for process I, okay? D sub I is the period of process I. And you can take a ratio of those two values, T sub I over D sub I, and that is the fraction of the CPU time used by process I, okay? U is defined as the CPU utilization. And this gives us the sum. So this says that the sum for I goes from 1 to n, where n is the total number of processes. The sum of all of those processes CPU fractional time, CPU ratio, if that is, that's U. So if U is 1, then the CPU utilization is 100%. If U is less than 1, then the CPU utilization is less than 100%. And if U is greater than 1, the CPU utilization is more than 100%. And if the required CPU utilization is more than 100%, what does that mean? There exists no schedule of those processes which is feasible. Correct? So feasible means that U is less than or equal to 1. Okay? EDF is always going to give us a feasible schedule as long as U is less than or equal to 1, as long as 1 is available. RM, the rate monotonic algorithm that we looked at first, is not going to give us a feasible schedule necessarily. But again, these are what's the word I'm looking for? Through testing, it's been determined that generally speaking, as long as U is less than approximately 0.7 or 70% utilization, then RM will generally give you a feasible schedule. Okay, but it's not guaranteed even at that level to give you a feasible schedule. So it just means more often than not, you'll get a feasible schedule out of the rate monotonic algorithm if the utilization is below 70%. Required utilization is below 70%. All right, I'm going to skip talking in detail about section 3.5, but that doesn't mean you're not responsible for it. You do have to read that section. And 3.5 does a lot of work to answer your question about what Windows 10 does, because in the real world, you usually use a two-tier approach at least, because you're going to have real-time processes and you're going to have interactive and batch processes, and they need to be treated differently. So generally, you do real-time processes and you give all of those priority and you have a schedule for real-time processes. And then you have batch and interactive processes that are kind of secondary. They don't have to meet a hard deadline, and you use a different algorithm or set of algorithms to process those. 3.5 kind of covers that material. All right, any questions? Okay, so I know a couple of you have already asked me about it. Yeah, exercise 3, I think it is. Exercise 3 is due tonight. Is that right? Or tomorrow night? You guys would know, right? Tomorrow night, before midnight. Okay, so if you haven't started working on that, I think you can ask your colleagues, your classmates, that it's not necessarily the most straightforward thing. It's not super easy. And you kind of have to get your mind right about the concepts that you're tackling while you're doing it. Okay? And there is at least one thing that you kind of have to look up and figure out how to use. All right, so all that being said, don't wait till tomorrow. Okay? All right, I'm done. I'll see you guys next week. Yeah, we need to talk about having a test at some point. I know. We need to look at the schedule. I have a sneaking suspicion that it's coming up. October 7th? Okay.